High-powered laser systems are making their way into more and more industrial applications. From cutting steel, to drilling via holes in silicon, to marking plastic, a whole range of processes now make use of the laser to produce results not previously practical. Advances in fiber lasers in particular have made laser systems with powers of many tens of kilowatts a common tool available to commercial users. However, the ever-growing demands for efficient productivity require that the laser process be stable and predictable. Just as with any tool used in precision manufacturing, the industrial laser needs to be monitored so that peak performance can be maintained. Even merely detecting a drop in some predefined laser parameter and having that trigger a call for preventive maintenance can save a lot of money, especially when compared to the cost of downtime and scrapped parts. In very general terms, a given process is designed to bring the beam to a specific power density in a precisely controlled location. That means that any change in either power or beam geometry at the target location can affect the process. That might mean, for example, a drilled hole that does not go as deep as it should or goes too deep, or an illegible serial number marked on a jet engine blade, resulting in scrapped parts. With ever-increasing power levels in today's industrial laser beams, heating effects on the laser's optical components, such as a focusing lens or a window, can cause a shift in the focal point location, moving it closer or farther away. It's easy to see how such a focus shift can critically change what the process is doing and where it's doing it. To ensure a consistent process over time, the relevant laser parameters must be measured as a function of time. Which parameters are critical to a given application, and what response should be triggered if one of them deviates outside the relevant limits, depend of course on the detailed needs of the application. How to implement such monitoring is where Ophir's expertise might be able to help you. Power or energy can be measured with a suitable sensor in several ways. Sampling a fraction of the beam power near the laser, periodically interrupting and measuring the full beam near the laser, periodically interrupting and measuring the full beam near the target location. Sensors can interface directly to a host controller integrated inside a system, or a human operator can periodically insert a sensor into the beam path to take a measurement manually. Many industrial laser systems use a combination of the two, where an operator periodically fires the laser into a sensor, and the reading from that is used to automatically self-calibrate a small sensor inside the system near the laser, for example. Ophir offers sensors that can measure a few picowatts, 120 kilowatts, or anything in between, so all options are open. Focal spot size and location, along with a whole host of beam characteristics, are typically measured using a beam profiler, either CCD camera-based or scanning slit-based. The choice involves many important trade-offs, since each type has its advantages and disadvantages, and it will be the myriad details that'll determine which solution is best in a given situation. Note that both interrupt the beam. Ophir recently introduced a non-contact beam profiler system called BeamWatch. The concept is based on a physical property of light known as Rayleigh scattering, where the highly concentrated light around the laser's beam waist is scattered off air molecules in its vicinity and captured by the camera. This allows for an analysis of the laser's waist without coming into contact with the beam. The result is a beam analyzer that works online without interrupting the process, with no water cooling required, no moving parts, and no upper limit in the power of the laser being analyzed. And since it's a camera-based system, it provides data up to 15 times per second. This allows the user to see more time-based characteristics of their laser system. The realities of modern industry are such that production facilities must constantly increase throughput at less cost, with less scrap, and with minimum downtime. The application of new advanced technology in measurement devices can help both designers and users of industrial laser systems to optimize and control their processes so they can accomplish these goals and achieve consistently good results, both in quality and quantity. If you're involved in any laser-based industrial application, We hope this short video has shed a little bit of light on issues you might be facing. For more in-depth information on this subject, we invite you to download our white paper at the link below. Please feel free to contact us either directly or through your local Ophir representative to see how we can help you with your application.